Good morning. My name's Jerry Metcalf. I'm the Business Development Manager for Cinch in Europe here, along with my colleague Ryan Marshall over here, who's the Business Development Engineer. We're going to talk to you this morning a little bit about the problems in the interconnect world, which designers very often have to solve. So within the systems which you guys tend to work on and design, inevitably in the higher end, high performing applications, you come across all these factors that you have to overcome. Vibration in particular, if you have connectors involved, you can't have discontinuities. You might have a high mating cycle requirement. You might have a high shock requirement, potentially high degrees of temperature gradients or variations in temperature or extremes of temperature. You may have to fit a device within a particular space envelope or within a particular weight envelope. You may have a certain life cycle cost target to meet, not just the sticker price of the part, but also potentially the cost of any servicing within your equipment. You want to make the part as user-friendly as possible, make it easy to maintain, etc., etc. But these are all factors which design engineers have to overcome. And very often within applications such as these, where you have the high-end server farms, where they have expensive chips, they don't want solderless connections, soldered connections or crimp connections. They want a pick-and-place type device. You may have extremes of environments such as on satellites, in space, or in the nose cone of a fighter aircraft. Certainly with parts being launched into space, you've got extreme shock and vibration on the launch vehicle. As in the picture on the bottom right there, you might have a high impact shock as the device is landed on Mars, and that is the ExoMars rover. We've got some parts inside that. So these parts have to tolerate the shock of launch, the vibration going through the atmosphere, minus 270 degrees in space for X number of months, however long it takes to get to Mars, and then the shock of landing and re-entry and landing, and the parts have to function right first time and have a high degree of reliability. So the solution which Cinch offers as a technology we call Synapse. It's a technology which has been around for around 30 years or so. It's a TRL level 9 as far as the space industry is concerned, so it's a mature technology, it's a mature product. The contact consists of a molybdenum wire gold-plated wound button, which is a contact which is held inside typically a polymer substrate. You can appreciate from the scale of this, the device on the left there is probably about 1.5 inches square, something of that sort of size. So the size of the button, you'll be hard pushed to see it sitting in the palm of your hand. But as with all matters in the electronics world, things are getting smaller every day. High density connections are required. This technology is used in a number of different formats. So you have potentially sockets for land grid array chips in the top left. It can be embedded into and alongside flex circuits and be used as board-to-board jumpers. It can be used as an interposer between specific devices and a PCB. And it can also be used to go in between PCBs as an interposer from board to board. And where we're talking a single button device, you're talking a 0.7 mil thickness typically. So it's the thinnest interposer that you'll find on the market to go from board to board jumpers. Other stacking devices typically are at least sort of 5, 6, 7 mil high, something like that. This you can get down to 0.7 of a millimeter. So the button is sometimes used in conjunction with either a plunger or a spacer, which gives it the benefit of either having a thicker device if you need a thicker device. The plunger also is useful if you have multiple matings. The plunger will take a lot more wear and tear than the button itself. And you can use the plunger and the spacers in conjunction with each other and different combinations of to achieve different interconnect types of points. Something Synapse is particularly useful for is mixing and matching different connection types. You see on the left-hand side of the bottom middle picture, That is where you might have a power distribution point within the circuit board. So underneath you'd have a power feed coming through a single pad with the larger buttons, multiple buttons, which you can each take up to 6 amps off to different parts of the PCB. On the right-hand side of the center picture, you can see a signal array where you'd have single buttons going for separate single signal lines. And in the middle you have RF points where you have RF signals coming through a shielded RF array. And Synapse can be used for all of those different kinds of technologies, and most importantly mixed into a single device, which, as I said earlier, can be as little as 0.7 millimeters thick. The materials that we use within the technology, there's nothing particularly exotic in there, so we never have any issues with supply of materials or shortages. We've chosen fairly industry standard materials, but they perform very well. The insulator can be a variety of materials. It depends upon the application, and it depends upon the volumes that they're required in, whether we mould them or machine them, and also sometimes the temperature required, or sometimes the impedance of the device that's required. So the insulators, the material will tend to vary more, but the contacts and plungers and so on, they're always consistently readily available materials. The Synapse devices themselves can be used into pretty much any configuration. When it comes to board-to-board connections, you can have the mezzanine arrangement, the right-angle arrangement, or the coplanar arrangement with a Synapse jumper in between. And we offer flex circuits with Synapse embedded in. In this particular example, you've got a low-profile Synapse device on the left-hand side and a higher profile stacking device on the right-hand side. If you're thinking about using such a device, the kinds of issues to consider are the number of contacts that you need, so the number of conducting lines that you have in either side of your boards or your device to your board, what kinds of types of devices you're connecting up, how tall they are. So you may have to have a set height between your PCBs. What the mating surfaces are of the devices on the boards, how you're going to compress the device, the operating temperatures and the electrical factors. I'm going to show you, some of the data that we have, but don't worry about trying to remember things. If you see Ryan or Tash here at the front afterwards, we can email you a design guide and a data sheet straight away today. Alternatively, you can pick up one of these crib notes from the stand, the Powell stand to my left over here. Yeah. So, in terms of the number of contacts and the types of contacts that you want, you have to think about the area that you have to work within. That may be dictated by the devices on your board, by the size of your board, by other fixings, and so on and so forth. Think about the functions of the contacts, whether you want to conduct power or signals or RF lines. If you think in terms of a 0.5 mil button per signal, would be required for the signal channels, 1 mil button per 6 amps of power for the power lines, and the size and complexity of the RF arrays that you want in there. Very often we do the circular arrays which you see in the illustration there, but equally we've put them in a myriad of different styles of shielding. And the signal data channels are typically in square arrays, as you see on the bottom right there, so that you can have pairs matched up for shielding. For the mated height, again, don't try and read this table. If we email you one of the data sheets, if you need that, you'll find this table in here. But essentially what it's showing is that for the different contact configurations, be they just a button only, you can go down to 0.7 mil. If you have spacers involved, you can go 1 inch plus. About the longest device we've done is about 1.5 inches. And that was quite a narrow device, and it goes underneath the sensor in a scanning array radar. So not particularly a PCB to PCB connection, but that's more a sensor being connected to a PCB, hundreds of them in this scanning array. And they have to pass through various other electronics to reach down to the board, so we ended up with quite a long device. As you can see in the photo here on the right, there's a device. This device is the Synapse device in this particular case, and you can see the locations on the PCBs that it connects between. And These are examples of some of the thicker stacking type Synapse devices that we have available. When you're thinking about the parts that you're trying to make together, think about the pad design on your PCB. Again, this is a solderless, crimpless device, so you can have vias there if you want, but we'd recommend a pad of 15 to 30 microinches of gold over nickel. You can have the open vias there if you have that for other reasons in your PCB. This is only for use with a land grid array in this particular kind of format, not a ball grid array. You do need the land grid array. And then you can think about the pad spacing, so you can get down to about a 1 mil pitch in European terms, or 20 thou pitch with the smaller devices. And with that, you can fit in roughly about 1,000 contacts in a space that's a little over an inch square. You do need a way of compressing your device onto the PCB with a Synapse device in between, but you can make use of the heatsink as part of the compression device in the case of having a chip being pressed onto a board. We've got an example at the moment where this is being used as a heatsink, both top and bottom. So you're not adding extra parts, but you're dual using the components that have to be there anyways, both the compression device and the heatsink. With the lower profile devices going from flex to board, you typically just have a plate, and depending on the length or the width of your flex circuit and the length of the plate on top, you might have 2 or 3 bolts coming through, so you can maintain the right amount of pressure on the device at all parts along all stages of the device. Check out the data sheets and either the flyer there or the design guide that we can send you to pick up on some of the environmental performance figures, the electrical performance figures, mechanical. We've got values in there that we know we meet comfortably, but equally we've had extremes requested of us. So in the case of shock, we've tested for 22,000 G. That was for a missile application, and the device passed absolutely fine. So if you have specific, come sit down, come in. So if you have specific requirements, take a seat, come in, it's fine. So if you have specific requirements in terms of any of these factors, get in touch with us, let us know, and we can do some testing and give you a test report, and you'll see whether the part meets your requirements or not. But the figures that you'll find in the data sheets are deliberately conservative, but they do perform beyond those. So the two documents we can email you, or they're on our website. The brochure on the right here, that has details and sizes of some generic parts that we have in distribution stock. The design guide on the left-hand side covers all the matters I've just been talking about, and they'll give you more of the parameters that the device meets. So the Synapse technology is manufactured here in the UK. It's also manufactured in our Mexican facility out in the US. So for any military type applications where there might be sensitivity over the data, it can all be kept here in the UK. You've got a local team in Ryan and myself who can respond to and support inquiries. And all of the manufacturing capabilities are, we don't rely on overseas supply for any of it. It's all based here in the UK. So generally, we'll have a turnaround time for a bespoke part. We'll send data and drawings out within a week or so. Depending on the complexity, we can make prototypes within a few weeks, and then we can get geared up for a production run within a matter of months. And the production run can depend on the size of the parts and the volumes of the parts that you need. We might either go for machining parts for quick turnaround early on, and then move to moulding if the volume warrants it or the size warrants it. And we can talk to you about that, about your specific needs and what you need from us. So a couple of success stories here. This is based on one of the stacking style connectors that we have in distribution. However, in this particular case, the customer had to have a mix of power, signal and RF lines all going through a single device. And you can just about, I hope, make out on top of the device here the various arrays that we used. In this particular case, you've got power on the left-hand side with the larger buttons and signals on the right-hand side. We were able to embody all of these requirements into a single device, rather than the customer previously had about 3 or 4 different interconnects, there. And there you've got a time scale for that particular development. So to summarise, Synapse is a high-density, solderless and encryptless connector technology, which is at technology readiness level 9. For the space game, that means it's mature, already on systems, it's orbiting the planet, it's all around us already. It's, as you can see from the photo here, it's highly customizable and adaptable from very thin types of devices, with lower density to very high density to very tall, with combinations. It's highly customizable. It's a high reliability solution. It is a technology that's renowned for working when it has to work and not failing, which is why it's on things like the ExoMars rover and on satellites. It's difficult to get to those systems and service them. Equally, it's on several missile systems because the device has to survive high impact, for example, so the missile can function properly if it's supposed to function beyond initial impact. You can put different kinds of signals through the same device. We can put in screens to separate the devices, metal screens through the thicker devices. We can work out how to distribute power from board to board through a Synapse device. It's proven to survive in extreme environments: high shock, high vibration, high temperature variation, high humidity. Pretty much anything you can throw at it, the Synapse technology will survive. If you need examples quickly, have a look at the catalogue, and you can take a look at distribution and find some devices in there. Equally, if you've got a specific need, talk to Ryan or myself, come to the Powell stand on your right there and have a conversation with us about your specific needs. Okay. Are there any questions for now? Otherwise, I would invite you to come to the stand and have a conversation with us over there. Thank you. Thank you very much.